All right, welcome everyone. My name is Anthony Taylor. I'm a fourth year mechanical engineering student, and this is a video explaining the double slit experiment, why it's important, give you some of the background, and kind of the things that came out of it. So just to start, this is Thomas Young. He's a young British mathematician and physicist, or he was anyways. Around 1800, he came up with an experiment to observe light, and he found something called an interference pattern. And he postulated that this interference pattern could only be caused by the fact that light was behaving as a wave, and that was very controversial at the time and a radical way of thinking. And so just to explain the experiment here, basically you have kind of a box. Imagine this as an enclosed space, and we've got two, or I should say three walls. So a box with a hole allowing light to come in, and then there's an inner wall with two slits in it, and a wall where we observe what happens when the light hits that. And so at point A, the light comes in and creates an initial wave pattern, and then at point B and C here, the light goes through each of the slits and creates another wave pattern. And then we have something interesting happening here, where the two waves sort of meet, and we have some interference going on. And this can be observed with water as well, which is obviously wave-like. And anyway, what happens is when it hits the final viewing wall here, we get what's called an interference pattern. And just to explain why that is, if you can imagine the types of interference that we're going to get two. One is constructive interference and the other is destructive interference. And as the name suggests, constructive interference is when the wave patterns add one another. And so what happens is the crest of wave C here and the crest of wave B combine and join and add together, and then the troughs do the same thing. So the amplitude ends up being larger, and conversely, destructive interference is exactly the opposite, where the crests and the troughs sort of meet up and cancel each other out. And so the result is bright spots and dark spots. And so if you've got light coming in, a dark spot is where you have destructive interference, and a light spot is where you have constructive interference. And that's a pretty good indication that you've got a wave-like behavior. And this is just another look at that sort of phenomena. And this is actually what it would look like here. So it's particularly bright in the middle, and it sort of scatters and dissipates towards the edges. And that's pretty typical for a light interference pattern. So this is something that was pretty cool to observe at the time, more than 200 years ago. And people since then have always been trying to explain it. And so we've got this guy here, James Clerk Maxwell, who's a Scottish scientist, and he's mainly known for his work in electromagnetism. But he postulated that light is in fact a wave on the electromagnetic spectrum. Yeah. And then you might know this guy, Albert Einstein. And well, he did some work, particularly with the photoelectric effect and explaining why that occurs. And he came up with that light is not just a wave, but it's a photon particle, a particle that's like a photon, that's called a photon, and basically that's he described as an indivisible packet of electromagnetic waves, which may look something like that, I guess, if you could sort of look at it on that kind of scale. And so we have these kind of interesting sort of theories. So one is a wave, one is a particle. Well, which is it? Maybe it's a wave-like particle. And so if we did our double slit experiment with particles, we might expect something like this. And if we shot the particles in through the slits one at a time, we would expect to get two line formations, because particle by itself isn't going to interfere or interact with anything. But that's not actually what happens. So when we shoot individual photons through the double slit experiment, we actually observe the wave pattern, the light interference pattern, which means it's a wave. But if it's an indivisible particle called photon, how can it be? How is it going, is it splitting and going through together at the same time? And this just completely baffled people for quite a while. Scientists didn't know what was going on until we sort of came up with this. And this is Schrodinger's equation here. We've got the quantum wave function. And what this does is it says that it sort of is a tool that we can use to accurately predict the probable position of the light particle. And that's kind of what this distribution curve is here. And that the two guys that sort of came up with that were, well, this is the Copenhagen interpretation, Danish physicist and German theoretical physicist Niels Bohr and Werner Heisenberg came up with this. And basically they said that the wave function doesn't physically describe anything, but it only purely describes the possibility of where that photon or particle might exist. And it sort of carries the possibility of infinite trajectories along where its starting point and end point are, and only once that you observe it, then that its true trajectory is revealed. And this is interesting because it works. It works with real things, and it's something that is hard to physically understand and conceptualize, because although we're using a wave function, we're not actually describing anything physical with it, not directly. And yeah, so these guys came up with that, and it's used today, to make accurate real predictions of the real physical world. But it isn't the only interpretation. I'm not going to cover other interpretations in this video, but it is interesting to see that there is a discrepancy between what we're observing, what's happening, and what we're able to do with that. All right, well, thank you for watching. I hope you found this video interesting, and we'll see you next time.